Welcome to UGC lecture series Linear Integrated Circuits. Today in this lecture we are going to discuss about the integrator circuit and sample and hold circuit. In the last session we have discussed about the differentiator and we have just started the integrated circuit, and the integrator performs the mathematical operation of integration. It is mostly used in analog computers, ADC converters and wave shaping circuits. And look at this circuit. This is the ideal integrated circuit in which the input signal is given to the inverting terminal, and from the output there is a capacitor connected to the inverting input terminal. So, this is the feedback capacitor. So, you can write it as CF and the input resistance as R1. So, we have derived the equation for the output voltage of this integrated circuit in the last session. So, we have applied KCL, Kirchhoff's current law, to this node. Consider this node as A, consider this node as A, apply KCL, consider this current as I1 and this current as IF. This is CF, since it is connected in the feedback path, this is CF and this is R1. So, KCL gives you an equation I1, the current flowing towards the node. The sum of the current flowing towards the node is I1 plus IF is equal to 0, since this IB minus is equal to 0 because the input resistance is assumed to be infinity for this operational amplifier. So, KCL at node A gives you I1 plus IF is equal to 0, in this case it is IB minus, and I1 can be written as VI by R1 plus IF can be written as CF dV0 by dt is equal to 0. So, VI is equal to dV0 by dt is equal to VI by R1 CF. You will get a negative sign here, and we have to derive an equation for the output voltage of the integrator. It is in differentiation terms, so you have to cancel out this differentiation by using an integration. So, take integration on both the sides with respect to the time. So, this is constant R1 1 by R1 C1 integral of VI dt. So, this gives you an equation V0 is equal to minus 1 by R1 CF integral dVi dt. So, this shows you the output of an integrated circuit is the integral of the input voltage with respect to the time, and the constant the time constant is minus 1 by R1 CF. R1 is the input resistor and CF is the capacitor connected at the feedback path. So, when you take S domain, V0 of S divided by Vi of S, which is nothing but the gain of the integrator, which is given by minus 1 by R1 CF S. So, if you take S domain, you have to include S term for the capacitor alone, because this is going to change, the capacitor is going to change according to the frequency, and S is nothing but the frequency term. S is equal to j omega. If you substitute S is equal to j omega, it is 1 by R1 CF j omega. We know that omega is the angular frequency 2 pi f. After substituting 1 by R1 CF j 2 pi f, this equation gives you A is equal to 1 by minus 1 by j R1 CF 2 pi f. If you take mod for the gain of the integrator, you will be getting 1 by R1 CF 2 pi f mod value, and here the negative sign will go off and imaginary term will also go off. So, this can be represented by FB by FA, where FB will be equal to 1 by 2 pi R1 CF. So, this is the gain of the ideal integrator. Ideal integrator has only the input resistance and the capacitor at the feedback. From this circuit we have derived the output equation, which is the integral of the input voltage with respect to time. And if you take S domain for this equation, you will be getting the gain of the integrator as FB by FA, where FB is 1 by 2 pi R1 CF. So, here if this is the frequency, then if correlate these two frequencies FB and F. F is the frequency of the input signal. When you look at the graph, in x axis it is drawn for the frequency of the input signal, and in y axis it is the gain of the integrator. So, when the frequency is 0, the input signal is signal's frequency is 0, what happens to the gain of the integrator? If you put 0 in this equation, if this is 0, then the gain will be infinity, but practically it is not actually infinity, it goes to the saturated value. So, which is depend upon the input signal, whichever the polarity of the input signal given to the negative or a positive terminal, then the corresponding saturated value will be the output of the integrator. And if the frequency is 0, then what happens to the capacitor is, capacitor is actually for the lower frequency the capacitor will be very high. So, this there is no feedback path between the output and the input. So, it is only, there is no feedback. So, it is acting as a open loop configuration, and in open loop configuration we know that according to the input voltage, whether the input voltage is given to the negative terminal, which is high, then you will be getting a negative V saturation, or if the input signal is given to the positive terminal, then the output voltage will be a positive saturation value. So, the same way in the gain of the integrator, you will be getting a saturated value when the frequency is 0, since the capacitor will be acting as an open circuit in this integrator circuit diagram. And this is the disadvantage of the ideal integrator here. Here the gain should not go to infinity, or it should not saturate for an integrator circuit. So, we have to do some compensation. So, we are going for the practical integrator circuit, where the only difference between the ideal integrator and the practical integrator is this resistance RF, which is connected parallel to the capacitor CF here. So, the remaining connections are the same. The signal V in is given to the input terminal, negative input terminal, through the resistance R1, and here this is R compensation, which will be connected, which is always connected to any operational amplifier circuit to compensate the bias current. It is one of the factor which is affecting the offset voltage. The output voltage, there will be some output voltage in the range of millivolts or nanovolts according to the construction of the operational amplifier, maybe maybe because of FET amplifier, or it may be a BJT amplifier. It is depend upon the FET or BJT. You will be getting the output voltage in the range of millivolts or nanovolts for 0 input voltage. That is said to be the bias current, and due to the bias current you will be having some output voltage even if the input voltage is 0. So, to compensate this effect, we are connecting a resistor to the positive terminal here, and that is said to be R compensation. So, this is going to compensate, this is going to nullify the output voltage for 0 input voltage because of this bias current, which we have discussed earlier as DC characteristics of operational amplifier. So, the difference between the ideal integrator and the practical integrator is just the resistor RF is connected at the feedback path, and it is parallel to the capacitor CF. So, for which if you derive an equation for the output voltage and as well as the gain of the integrator, we will be notifying that the output of the gain of the integrator is not going to saturate for the lower value of the frequency. So, we will see the derivation now. So, here you consider ZF as the parallel combination of RF and CF. So, what is the parallel combination of RF CF? We have to calculate. So, RF into 1 by CF, and when you take into the S domain, then you have to include S parameter for the capacitor, divided by RF plus 1 by CFS. So, which is simplified as RF by CFS divided by RF CFS plus 1 by CFS. These two terms will get cancelled. So, ZF will be now RF by 1 plus RF CFS. And what is ZI? That is the input impedance. Input impedance is just R1. So, now you can write the output in terms of S domain, output divided by the input in terms of S. So, this is actually minus ZF by ZI. So, we know that ZF is derived as RF by 1 plus RF by 1 plus RF CFS. This is ZF minus ZF by ZI is RF by 1 plus RF CFS divided by ZI is actually R1. So, you can straight away write it here as R1. So, this is your gain of the practical integrated circuit. If you take the modulus of the gain, I am replacing V naught of S by Vi of S as A, then you will get RF by R1 divided by 1 plus, substitute S is equal to j omega and omega is equal to 2 pi f. So, you will be getting here RF CF 2 pi f mod value, and if you take the mod value, then you have to write like this: a square plus b square in the denominator, root of a square plus b square in the denominator, which gives you the negative sign will go away and j term will also go off. You will be getting 1 plus, keep f as such, that is the frequency of the input signal, f divided by 1 plus this this terms RF CF 2 pi can be treated as 1 by FA, the whole square. So, this is the value of the gain when you take the mod value. So, here this is the frequency of the input signal, and this is a new frequency term which you have got when you connect the feedback resistance parallel to the capacitor, feedback capacitor CF. And so, this gives you F is equal to 1 by 2 pi RF CF. So, this is FA. Now, if you correlate the frequency of the input signal and the new frequency term FA, so what happens to the gain of the practical integrator? Okay, for F less than FA, if you see the practical the frequency response of the practical integrator, if F is equal to 0, if F is equal to 0, if you substitute F is equal to 0 in this equation, so you will be getting only 1 in the denominator, and the modulus value of the gain of the practical integrator will be equal to RF by R1. The same is marked here, this is RF by R1 here. This is actually marked, this is RF by R1 dB, and if F is equal to FA, say this is FA, what happens in the equation? If F is equal to FA, you will be getting 1 here. So, root 1 plus 1 2. So, RF by R1 divided by root 2, and that is nothing but 3 dB lower than the value RF by R1. So, it is marked as RF by R1 divided by root 2, which is nothing but minus 3 dB value at F is equal to FA. And when you increase the frequency beyond FA, what happens to the gain? So, this equation tells you that if F is increased beyond FA, this term will also be increased, and this higher term will be dividing the numerator now. So, the gain is reduced. That is what marked here. The gain is reduced at the rate of minus 20 dB per decade. For every 10 times increase in the frequency, the gain is decreased at the rate of minus 20. And this line shows the basic integrator response. We know that f is equal to 0 in this equation, which gives you the gain of the integrator infinity, but practically you will get a saturated value. So, this is marked here for f is equal to 0, and if f is equal to, say, this is fb, if this is fb, so if these two frequencies are equal, then you will be getting the value as 1. If you calculate in dB, it is 0. So, it is 0 dB in this case. So, since we want to make this saturated value to a numerical value, you are going for a practical integrator, and that is otherwise known as a lossy integrator, because this these two passive components RF CF parallelly connected RF CF behaves like a practical capacitor which dissipates power. So, it is otherwise known as a lossy integrator. So, this circuit gives you a gain as this equation, RF by R1 divided by root of 1 plus f by Fa, and for this frequency we are substituting 3 values. When f is equal to 0, what happens to the gain of the practical integrator? If it is 0, then we shown that the gain is RF by R1 in the response of the practical integrator, and if f is equal to Fa, then the gain is reduced by 3 dB from RF by R1, and if f is still increased beyond this Fa, then the total RF by R1 will get reduced, and that is what shown in the practical integrator response. This is shown here. So, instead of the saturated value, the gain is reduced to RF by R1 in that case, and this is actually the gain of the inverting amplifier. Since the signal is given to the negative terminal, you will be getting this equation RF by R1. So, if the frequency is very less, then the circuit will act as an inverting amplifier circuit, and we will see the design steps. If FA tells where the useful integration starts, FA is actually derived as 1 by 2 pi RF CF. So, here FA tells the useful integration starts. At FA, the integration started. If the frequency of the input signal is lesser than this FA, then the circuit will act as an inverting amplifier, no integration will result, and if f is equal to Fa, 50% integrated value will be obtaining, and if f is 10 times Fa, then you will get 99% accuracy in the integration. So, these steps you have to follow in the design of an integrator. First, you have to choose Fa, and for that you have to assume the value of the capacitor as less than 1 microfarad here. So, if Fa is chosen, then RF can be calculated, and then the frequency of the input signal must be 10 times of Fa. So, you will be getting 99% accuracy in the integration. And the next circuit is sample and hold circuit. This circuit is used to take the samples of the input signal and hold the sample until it samples the next sample of the input for a definite period of time. The time during which the sample and hold circuit generates the sample of the input signal is called sampling time, and the holding time is the time during which the circuit holds the previously sampled amplitude across the capacitor. That is said to be the holding time. So, this is the circuit of the sample and hold circuit. So, here the input signal is given to N channel enhancement mode MOSFET, and this is going to be acting as a switch, and this capacitor is sampling the input signal whenever the series of pulses is positive, and when the pulse is negative, then the capacitor holds the previously sampled amplitude of the input signal, and the capacitor's voltage is given to an voltage follower circuit. So, this has the output feedback to the negative terminal of the input operational amplifier, and this circuit is actually a voltage follower circuit where the signal is given to the positive terminal, and this voltage follower is otherwise known as a unity gain feedback circuit. This output follows the input, that is why it is called as a voltage follower circuit. So, how it is going to act as a sample and hold circuit is, the entire setup is, this capacitor is going to sample the input signal whenever the switch is on, and when the switch is on, the capacitor charges instantaneously to the input value, and if the switch is off, then the capacitor holds the sample whatever it is charged, it is getting charged for the input signal previously, and this capacitor won't be discharged through the operational amplifier. Since this op-amp is working as a voltage follower, it is having a high input impedance, and this voltage follower is giving you the voltage across the capacitor at its output, since it is going to follow the input voltage. So, the input voltage is given to the drain terminal of the enhancement mode MOSFET, and to the gate the control voltage is given. The control voltage is, whenever the control voltage is positive, the gate is on and the switch is on. So, when the switch is on, the capacitor charges instantaneously to the input voltage, and when the control voltage is off, then the switch is also closed. The capacitor will not charge at that period, during that period, and this holds the previously charged amplitude of the input signal, and this is actually acting as an input for the voltage follower, and the output is nothing but the input of the voltage follower circuit. And this waveform tells you how the capacitor samples and hold the input signal according to the control voltage given to the MOSFET. This control voltage is given to the gate of MOSFET, and input signal is given to the drain of MOSFET. Here also you can use an voltage follower circuit if the input signal is very low. If it is a small signal, then you can use a operational amplifier as a voltage follower mode. Since the voltage follower is having high input impedance, it will not be acting as a load to the AC signal, small signal. So, you can use a voltage follower circuit in between the input signal and the MOSFET. Okay, this is consider this as an input signal to the MOSFET, and this is the control voltage to the gate of the MOSFET. It is actually the series of pulses, and whenever the pulse is positive, then the capacitor charges the instantaneous value of the input signal. So, until the pulse is positive, the input signal is charged, the capacitor is charged instantaneously to the input signal, and when the pulse is negative, it holds the maximum charged value across it, and when again the control voltage is positive, then the capacitor charges instantaneously to the input signal amplitude, and if it is negative, then it holds the maximum amplitude of the previously charged input signal. Similarly, it goes on, and so this circuit is called as a sample and hold circuit. The sampling period is the time taken by the capacitor charging the input signal. So, time taken by the capacitor during which the capacitor charge the instantaneous value of the input signal is the sample time, and hold time is the time taken during which the capacitor is holding the maximum amplitude previously charged is said to be the holding time. And the condition for the time period or the frequency of this control voltage is the frequency must be greater than or equal to twice the maximum of the input signal's frequency. That is said to be Nyquist criteria. It must satisfy the Nyquist criteria. The frequency of this control voltage must be greater than or equal to twice the maximum frequency of the input signal. So, it must satisfy the Nyquist criteria, so that if you reconstruct this sample and hold part of the voltage across the capacitor, then you will be getting a errorless input signal. If you reconstruct the sampled circuit, sampled signal, then you will be getting errorless input signal at its output if the control voltage must satisfy the Nyquist criteria. So, now you can try to answer the question, where is sample and hold circuit used, discuss the drawback of the ideal integrator. Why is the drawback of the ideal integrator, which we have seen, is if the frequency is very low, in the frequency of the input signal is very low, or you can say if it is 0, then the gain of the integrator will be saturated. So, this is the drawback of the ideal integrator, it should not saturate. So, we have connected a resistor across the capacitor in the feedback path, and this gives you the value of Rf by R1 as the gain of the integrator if the frequency is very low. So, if the frequency is 0, then the integrator will be acting as a inverting amplifier in that case. And why is lossy integrator important? That is what we have discussed now. So, the answer for these two questions are one and the same. So, in this session we have discussed the ideal integrator, the limitations of ideal integrator. In the ideal integrator circuit, if we replace the resistor and the capacitor of a differentiator, instead of a resistor in the feedback, if you connect a capacitor in the feedback and the resistor in the input side, then that circuit is an integrated circuit. And we have derived the output of the integrator, and from which we have derived the gain of the integrator. And we have seen that what happens for the ideal integrator if the frequency is 0, and if the frequency is 0, then the gain of the integrator will get saturated. So, this should not happen. So, we have replaced, we have used practical integrator in that case. So, in the practical integrator, the only component we have included in the feedback loop is the resistor. It is represented by Rf. So, with this Rf, again we have derived the output equation of the integrator and the gain of the integrator, and we have assumed 3 values for the frequency of the input signal. So, if the frequency of the input signal is 0 in this case, then the output of the gain of the integrator is not saturated. Instead of saturation, it shows the value Rf by R1. So, if the frequency is 0, then the integrator will be simply acting as an inverting amplifier in this case. And if the integrator is, if the frequency of the input signal is equal to Fa, then the gain is lesser than 3 dB. It is reduced to 3 dB of its value. And if the frequency of the input signal is increased beyond the Fa, then the gain of the integrator is reduced at the rate of -20 dB per decade. So, these we have seen by deriving the gain of the practical integrator as we have derived for the practical differentiator. So, in the frequency response, we have seen the response of the ideal integrator as well as the response of the practical integrator, and we have seen the design steps of the practical integrator. So, here in the design step we have seen, first we have to select the frequency Fa, which is 1 by 2 pi Rf Cf, and if F is less than Fa, then the integrator will be acting as an inverting amplifier, and if F is equal to Fa, then you will be getting 50% of the integration, and if F is 10 times of Fa, then the integrator will give you 99% accuracy in the integration. So, we have seen all these things in the in integrator. And the next circuit we have seen is sample and hold circuit. This is one of the application of a non-linear operational amplifier, because why it is non-linear is if the input is changed, then the proportional we are not getting the proportional change in the output. It is actually the sample and hold circuit. This circuit is going to sample the input value according to the frequency of the sampling pulse, and it holds the circuit whenever the control voltage is negative. So, this circuit is used for analog to digital converter circuits mainly, and for digital communication. And These are the references. Thank you.